easy to compute, to calculate. I mean, you see these states actually. Oh, you don't need something as you don't need them all, of course, to form a basis. You can start just with the fiducial or standard squeeze state, which is if I psi 0, it's denoted by, I think, normalization constant.
Yes, that's right.
Should I?
Okay, this is the standard squeezed, standard coherent state. It's an eigenfunction for the harmonic oscillator with mass and frequency equal to 1. And then you define psi z by t hat z psi 0, where this is a Heisenberg-Weil operator. Okay, so you get the whole family, an infinite family of coherent states. These can be used as a basis. Yeah, that's something.
I have a problem with the transformation equation on the top of the
which one?
Right at the top.
This one here.
I can't see any z on the right-hand side.
But z is xp.
Ah.
Oh, sorry, I should have recalled my notation. Yeah. This is xp. This is the phase space variable.
Right.
Yes, yeah.
As a vector.
Yes. Well, the integral is being taken over Rn. Yes. Oh, you know, I think most people here know that, that this is very appealing because it plays the role of a joint distribution, although although it can take negative values, except when psi is Gaussian. And that's a theorem due to Nelson. Janssen and Hudson, who showed that this is non-negative if and only if psi is a Gaussian. In all other cases, it can take negative values. So it's sometimes referred to as a quasi-distribution. There was a volume edited by Basil where a few years ago, there was a talk by Feynman, I think. He was talking about negative probabilities. I don't buy that because then you are playing on words, of course, because by definition of probability.
All he was doing was saying, I can't see any problem in using negative probabilities, provided it doesn't come out in the final result of probabilities.
He's absolutely right. By the way, this is also the symbol, the Weil symbol of the density matrix of a pure quantum state.
Of course.
And the symbol of a mixed state is a convex sum of Wigner transforms. I mean, this is a
density matrix.
Yeah, this is an absolutely essential object. I mean, and yes, you know. Well, okay, I'm not going to talk about density matrices and all the Weil calculus here, but I mean, it's a natural notion in Weil calculus. And as you discovered in a paper, which is that there's a fundamental connection with Bohmian.
Well, there's a fundamental connection with the von Neumann idempotence.
Well, yes,
and,
also as you pointed out, that's yes.
And the Bohm.
And yeah,
it's all part of one structure.
This would be very interesting to discuss how you can start from nothing, phase-space ellipsoids.
Can you briefly say how the connection to Bohmian mechanics is? Can one say this in 2 words or 3?
2 words.
2 words, good.
No, I don't think I can say it in 2 words. What do you think?
Characteristic functions.
Yeah, well, it's characteristic functions, but then what you... Oh, yeah. The idea is that you take the distribution, the Wigner distribution, you then form a marginal distribution by integrating over x. X, so that you then find that the probability is the transport of that marginal distribution. You then work out a mean momentum with that distribution, and you find that that mean momentum is exactly the Bohm momentum, and then you look at the transport equation for that momentum, and it's the Schrödinger equation.
So that must have then really something to do with optics.
Of course. Yes, of course.
But everything is optics.
Yeah, I think
It's true, eh?
of course, everything is optics.
Of course. That's what I've been trying to
And since optics is symplectic geometry, everything is symplectic. Yes.
I was
Yes.
very much surprised by Gromov's non-squeezing theorem. I didn't know that. Is there...
Few people have, even among mathematicians, have heard about that. Well, that was starting a little bit in symplectic topology, but it's very new, just 20 years old.
So it's a kind of shape preserving that happens.
Yes,
here.
yes. From my point of view, it shows, makes think at least, that Hamiltonian dynamics has a tendency to be less chaotic than perhaps people think it is. I don't know what it is. But of course, atmospheric motions are dissipative more or less. I don't think you can call them Hamiltonian. No, sorry, they're not conservative, of course. So it does not apply to the tradition.
Is there any way to give a rough idea how the proof goes? Or is this too
It's
complicated?
horribly complicated.
Okay.
In the general case, yes, it takes 20, 30. How it goes in, well, to prove it in the case of linear transformation is not too difficult. You diagonalize and you compare the spectra. You diagonalize, actually, not in the usual way, but you take, there's something which is called the Williamson's theorem. It goes back to 1937, but some people say that actually it was implicit in Weierstrass's work already. It says that suppose you have a matrix M which is symmetric and positive definite. But of course you know that you can diagonalize it in the usual way. But Williamson proved that you can diagonalize it using symplectic matrices. And the D here is of a very special sort. It's of the type lambda 0, 0, lambda, where lambda just consists of lambda 1 and lambda n, where the lambdas are the eigenvalues of Jn.
Okay.
And using this, actually, you can prove Gromov's theorem in the linear case. Sorry?
Is it inverse somewhere? Lambda inverse?
No, the lambdas which are here. No, the yes. The lambdas are yeah. Jn.
No, yes.
Yeah. No. Yes.
No, I just wondered whether it was lambda and lambda inverse in the reaction.
No. The lambdas are the eigenvalues. Oh, no, the absolute values of the eigenvalues of Jn. The same as I had written down there in my okay.
Reese,
Yes.
is the implication of what you're saying here is that if you find yourself a single particle in some Hamiltonian system, and you say you make a measurement and you combine that particle to one of your small volumes, and then you allow that to evolve classically, that there isn't any difference to quantum mechanics.
Precisely.
You don't even need a quantum potential.
Depends how you project.
But don't forget that instead. Well,